For this lesson, I want to go over problems where you have two objects interacting with each other, and therefore Newton's third law applies. But in one of those objects, or in some cases in both of those objects, you have force of friction involved. And in the past, we've actually sort of said, let's just ignore the values of friction, but now I'd like to actually go through how you would apply those and get actual values of friction in newtons. So here's an example, and I'd like you to take notes while we do this. So you have a photographer in New York who captures the image of a man pulling a chair. It looks like the man is pushing the garbage can. He is not. It's just the man in the chair. And the man has 25 kilograms, and the chair is 10 kilograms, and the man and the chair are accelerating at 0.25 meters per second squared. It does say that there is a 5 Newton force of friction between the chair and the pavement. So we'll start off with creating an interactive diagram. And so perhaps I'm going to use the color red for this one and start labeling these. And when you're doing your own, I'd like you to label those as well. I'm going to put the earth underneath here. And so the first question I ask is their gravity. And there's gravity between the man and the earth. There's also gravity between the chair and the earth. We have the pavement over here. And I could also say that there's gravity between the pavement and the earth. Secondly, I want to ask, is there a normal force? And yes, there is. There's a normal force between the chair and the pavement, as well as a normal force between the man and the pavement. We could say that there's a normal force between the pavement and the earth. That would be fine as well. All right, next question that I ask, is there a push or pull between the two objects? And there is. Between these two objects, it looks like there is a pull, so we call that an applied force. I don't see any more applied forces in any of these. And lastly, is there friction? And the answer is yes, there is. I tell you that there's friction between the pavement and the chair, and there's also friction between the man and the chair. So the key in all of this is I know that this object, these two are accelerating, and because they're accelerating, I know I cannot create balanced force diagrams because any sort of acceleration would be unbalanced. So I created an interactive diagram of my scenario. Now what I want to do is create those force diagrams. So let's start with creating a force diagram of the man. So I'm going to circle that man and just sort of see what sort of forces we included. So it looks like I have a gravitational force in here, a frictional force between his feet and the pavement. It looks like I have a normal force right here and applied force. So I'm going to keep on scrolling down. I'll be moving up and down. So here I have the man, and down. And so we did say he had a gravitational force. So I write Fg. Remember, it's between the man and the earth. I have a normal force between the man and the ground. And in this case, the man looks like he is pulling the object in this direction. So that's an applied force between the man and the chair. And I did say there was a frictional force. Okay, and we're going to determine what that frictional force. The frictional force is between the man and the ground. Okay, now I know this looks like it's a balanced force diagram. I'm going to adjust these vectors once I get the values so that I know how long to make those. Okay, I'm going to do the same for the chair. I know the chair has a gravitational force that's between the chair and the earth. I know that it has a normal force that's going to be between the chair and the ground. And in this case, the man is pulling the chair, but also the chair is pulling the man. So this is going to be the chair. And so my applied force is moving this direction because the chair is pulling the chair is pulling the man that direction. And so in that case, the chair is pulling the man back. And I said there was a frictional force as well. For this one, I actually do have the value. This was between the chair and the ground. And if I look up here, the value I was told was that there is a friction between, right here, it says the friction between the chair and the pavement, which is the same thing as the ground, was 5 newtons. All right, so that I know is 5 newtons. So we've got the value of one vector over here. So how about getting the rest of the values? Well, the easiest ones for me is always to get force of gravity. So I know I need to get the masses of these objects. So it looks like the man is 65 kilograms and the chair is 10 kilograms. I'll write that down for myself. I know mass of man is 65 kilograms. The mass of the chair is 10 kilograms. And I know that force of gravity, the formula that I always use for that one is mass times gravitational acceleration. So in that case, it's 65 kilograms times 10 meters per second squared. That gives me a value of 650 newtons. So I know this is 650 newtons. Because the man is not falling into the ground or the ground is not pulling up on him, I know for that reason these two are balanced. Okay? So this is equivalent to this one. So I'll just put one dash mark to show that for myself. All right, the next one is, let's do the force of gravity for my chair. Same thing, Fg equals mg. In this case, my chair is 10 kilograms. Force of gravity is 10 meters per second squared. You can use 9.8 as well. I'm just making my math a little bit easier. So I have 100 newtons of force. So in this case, this is 100 newtons. This is also 100 newtons. All right, now I know that I have 5 newtons of frictional force. I need to find applied force. So my suggestion is that choose the object or that you have the most information of in terms of how many newtons of force are on each vector. Here I only have 2 pieces of information. This one here, I've already been given 3 pieces of information. So I'm going to base my applied force on the chair, okay? So I know that applied force, I know that force equals mass times acceleration, but this, remember, is net force. So we've been sort of always saying, oh, but that's the applied force. In this case, because we do have the value of friction, you need to remember that this is a net force right here. So I know that my object for the chair is 10 kilograms. And when I see my acceleration back up here, the acceleration is 0.25 meters per second squared. Okay, so I multiply that. That's 0.25 meters per second squared. This works out to be 2.5 newtons of net force. Okay, so net force, remember, is force applied minus frictional force. Or you can say frictional force minus force applied. Makes no difference as long as you have a positive value. All right, so if I know that the net force is 2.5 kilograms, right here, 2.5 newtons. 5 newtons of force are being pulled this way. How many newtons of force have to be pulled that way in order for this to have a net force of 2.5? And the answer should be 7.5 newtons. How did I get this answer? Well, if I find the difference between these two, I should see a net force of 2.5. Okay, so 7.5 minus 5 should equal 2.5. Or I can say, oh, if my net force is 2.5, I have to add it to my frictional force. So I know that my applied force on my chair has to be equal to my applied force on the man. All right, so the man has, in that case, an applied force of 7.5 newtons. Okay, what does that mean about the frictional force of this man? So here, I also have to find the net force of the man. So in this case, the net force of the man is 65 kilograms times times 0.25 meters per second squared. Where did I get this number from? Remember, my acceleration, if you look up, was 2.5 meters per second squared. And I'll just show you where that is again. There it is, right there. So his net force, we're looking for the net force right here, should be, and I realize I need to actually calculate this, should be 65 times 0.25, which works out to be 16.25 newtons. All right, so this is my net force. What does that mean about my frictional force? And remember, frictional force is more or less, net force is applied force minus frictional force. So in this case, I know that my net force is 16.25 newtons. I know that my applied force, and I want to make sure that I get this to be just a difference. My applied force was 7.5 newtons, so Fa. And my frictional force has to be the difference. Remember, we're doing the absolute number. So in this case, my frictional force, if I do my calculations correctly, are going to be the difference between these. I should actually say the addition to them. So let me pause this for 1 second. So I need to ask myself, what value is going to give me a number that's going to be 16.25? And so the way I can do it is I can add these two together. So my number should be 23.75 difference, okay? Keep in mind it's always a positive value, all right? So I know that you might get thrown off with the different values. Perhaps what I should do is say, in this case, frictional force minus force applied. In that case, it would be frictional force minus 7.5. Now I'll erase the rest of it. Let's try that one more time, just because I know it will throw us off. Thanks for holding on to that. Okay, so that means we said frictional force minus force applied. So in that case, frictional force minus 7.5 newtons. And that equals to be 23.75 newtons. Okay, so that means that the frictional force is, let's see that, 23.75 was right. So that means that this is 23.75 newtons. All right, and that gives you all the values. So a couple things that are new. First of all, to highlight, gravitational force and normal force are pretty straightforward. Remember, choose the object that you have the most information from. This one we had two, a gravitational force, a normal force, and a frictional force. So that made it easier to find what the applied force was. In order to find the applied force, remember, you need to calculate what the net force is and find the difference between the two, okay? In this case, I knew the net force was 2.5. I had a frictional force of 5. My applied force had to be 7.5. I know that these two are equal, so I know this had a force of 7.5. And again, I needed to find out what the frictional force was. I needed to calculate the net force first. And by doing that, I could then find the